molecular formula and empirical formula. The second part will be looking at the relative atomic mass, relative molecular mass, and also we'll be looking at the compound, formulas of compound generally. So we wrap up with this chapter. Then after this chapter, we'll go to chapter 6. Chapter 6 is about moles. So we need to revamp the moles. It's very important in Cambridge IGCSE. Now let's start with what we have. The first one is the molecular formula. First, we want to look at, we say elements are usually represented with the chemical symbols. Every element. You write sodium is Na because its native name is natrium. You write lithium is Li. If you write chromium is Cr. If you write gold is Au. If you write hydrogen is H. So every element in the periodic table every element in the periodic table has got its own chemical symbol. It's got its own chemical symbol. Is that okay? Every element in the periodic table got its chemical symbol. Okay. So let's quickly take a look at what we have. We have elements. We have elements here. And we got some few examples and their corresponding symbols. We say lithium is number 3 in the periodic table. Okay? It has atomic number. Lithium has atomic number 3, right, in the periodic table. So it's in position 3 in the periodic table. The symbol is Li. Okay, so we have chromium, the symbol is Cr. We have aluminium, the symbol is Al. Okay, we have calcium, the symbol is Ca. We have gold, and the chemical symbol is Au, and sulfur, the chemical symbol is S. Okay, so these are some of the elements. Now let's take a look at more of elements. Okay. Now let's take a look at the several elements that exist at the atomic molecules. Several elements. The word diatomic means the one you write H2, for example, you write 2 beside them. You write the symbol, you characteristically put 2 as a substrate, as a small substrate beside it. We call diatomic. Di means 2. So let's take a look. That means they have 2 atoms. Diatomic means they have 2 atoms. So let's take a look at several elements which exist as the atomic molecules. Means that for every one molecule they have 2 atoms. Every one single molecule of that element has 2 atoms. One is hydrogen. The first one is hydrogen, okay, which is actually in the period 1 of the periodic table, and also, but not in group 1 anyway, but in period 1. So the first one is hydrogen, and then we have nitrogen and oxygen. Besides hydrogen, nitrogen, and oxygen, the rest of them are group 7 halogen group. The rest of them are in group 7. Is that okay? So we have nitrogen, we have oxygen. So hydrogen, nitrogen, oxygen, these are the only ones. The remaining 4, they are in halogen family, group 7 of the periodic table. We're going to look at periodic table to identify these elements. So the first 4 elements in the group 7, they're part of it. The fluorine, the chlorine, the bromine, the iodine. So these 4 elements in group 7 of the periodic table, which we call the halogen family. Okay, these ones are called the halogen. So these halogen, they are the atomic. These halogen, not all of the halogen, but the first 4 halogen in the group 7 of the periodic table, they are the atomic elements. And then after that, we have the basic one, which is hydrogen, nitrogen, and oxygen. So these are the first. These ones are not in group 7. This hydrogen, nitrogen, and oxygen, they are not in group 7. Okay. So these are the 7 atomic elements that we need to get familiarized with. Look at them in the periodic table. Take a look at the periodic table. We have hydrogen here somewhere on its own, not in group 1, not in group 2, not in any group. Okay, because these are transitional elements. All these ones are transitional elements. They are between group 2 and group 3 in the periodic table. Then we have the nitrogen and oxygen here, which belongs to group 5 and 6. Nitrogen is in group 5. This is group 5. While this oxygen is in group 6. And then the remaining 4 are in group 7. Group 7 in the periodic table, the halogen family. Remember, this is group 8 or group 0. You can call it group 8 or group 0. This one, the noble gases. They have 8 already in the outermost shell, so they do not need to react. Okay. do not need to react in order to get elements, or they do not need to undergo bonding in order for them to get elements or give out electrons, or to get electrons or give out electrons. They don't need to do that. So the 7 diatomic element, we can easily identify them. The 7 diatomic element, we can easily identify them, right? We have the hydrogen, we have the nitrogen, we have the oxygen, and then we have the fluorine, chlorine, bromine, and iodine. Is that okay? So we move on. We identified the 7 diatomic elements, right? We move on. So by diatomic means we write 2 as a substrate beside the symbol of the element. Okay? Now let's move on. Let's go to examples of molecular formulas. So we already said if you write hydrogen, you have to put 2 because it's diatomic. You have to put 2 as a small substrate beside it. Chlorine, same thing. Okay? So you can see water is H2O. These are the molecular formula or the chemical formulas of this compound. Methane is CH4, ammonia is NH3, sulfuric acid is H2SO4, and so on and so forth. Now let's take a look at what is made from each of them. Hydrogen is made of 2 atoms of hydrogen. Hydrogen as an element is made of 2 atoms of hydrogen. Chlorine, same thing, 2 atoms of chlorine. So when you say water is made up of 2 hydrogen atoms and 1. You can see it here, 2 atoms of hydrogen and 1 atom of oxygen. Even if you don't write 1 here, there's always 1. Okay, water is made up of 1 atoms of hydrogen, 1 atoms of oxygen. Even if you don't write it here, there's 1 atom of oxygen and 2 atoms of hydrogen. That's water. Now methane is made up of 1 atom of carbon, 1 atom of carbon atom, and 4 atoms of hydrogen atoms. Okay, 4 atoms of hydrogen. And then ammonia is made up of 1 atom of nitrogen and 3 atoms of hydrogen. Sulfuric acid is made of 2 atoms of hydrogen and 1 atom of sulfur and 4 atoms of oxygen. So each of these we can calculate their molecular formula. Okay, apart from the chemical formula that we've written, we can calculate their molecular formula. How we do that? We need to know their relative atomic mass. We need to know the relative atomic mass of each element. For element, we talk about relative atomic mass. Okay, for the compound or for the molecule, we talk about molecular formula. Okay, relative molecular formula. So if we're asked to calculate relative molecular formula, we know hydrogen is 1. So we simply say 1 times 2 atoms because hydrogen has 2 atoms here. So we say 1 times 2. Okay, plus sulfur is 32, so we just say 32 is the atomic number, relative atomic mass of sulfur, multiplied by 1. So no need to say multiply by 1, it's going to be same thing. Plus oxygen is 16, relative atomic mass of oxygen is 16, multiplied by 4 atoms. There are 4 atoms of oxygen here, so we multiply by 4. We're going to get 40. I think we multiply by 4, we're going to get 64, right? We're going to get 64. So then we have 2 plus 32, which is 34. 2 plus 32, which is 34, plus 64. Okay, plus 64. We get 98, right? We get 98. So we get 98. So the relative molecular formula for H2SO4 is 98. Relative molecular formula is 98. Okay. Similarly, we can do this one. Nitrogen is 14, and 40 times 1 is 40. So we just write 14 plus hydrogen is 1 times 3. 1 times 3 we get 3. So 14 plus 3 we're going to get, eventually we're going to get 17. Right. So for ammonia, the molecular formula, relative molecular formula will be 17. Similarly, for every other one is same. So let's just do one of same element. You know, this is a compound, this is a compound, this one is a compound. Okay, but let's take a look at the case of element. For water is 1 times 2, 1 times 2 because hydrogen is 1. So 1 times 2 atoms, it has 2 atoms, so you say 1 times 2 plus oxygen is 16. Relative atomic mass of oxygen is 16. Relative atomic mass of oxygen is 60. So 60 times 1 is 60. So you say 1 times 2 is 2, 2 plus 16, you get 18. So the water relative molecular mass of water is 18. Relative molecular mass of water is 18. Okay, so that's for water. Now we talk about hydrogen. We talk about hydrogen. Hydrogen is 1. 1 times 2 because it has 2 atoms. Hydrogen, the relative atomic mass is 1. So times 1 times 2, we get 2. 1 times 2, we get 2. So the relative molecular mass will be 2. Relative molecular mass of hydrogen will be 2. Is that okay? So it will be 2. So we can simply come and show that. We can simply come and show that. Okay? This one plus 16. I think every time lag, we lose a little bit of something. So that this one is 18. Relative molecular mass of water will be 18. Now for this one will be 1 times 2, which is 2. 1 times 2 is 2. Okay, we just put that. Chlorine is 35.5 times 2, so you get 71. 35.5, that's the relative atomic mass. Multiply by 2, you get 71. So that's that for that. We move on. Okay, now we go to say the table you've just seen. The table also shows that the molecular formula can be deduced from the relative number of atoms present, right? In the case of ammonia, you can see that ammonia contains 3 atoms of hydrogen and 1 atom of nitrogen, which means that we write the formula NH3. Is that okay? Now let's go to diagrammatical representation of chemicals. The diagrammatical representation of chemicals. Now sometimes we use model. We use diagram, models, drawings, and so on and so forth to represent or to deduce the molecular formulas of elements and also compounds, not only elements. So we look at that of elements, especially the atomic elements and the atomic compounds. Okay, for example, in the case of element, let's take a look at hydrogen. Hydrogen is diatomic, so which means for diagram, you just draw one circle to represent one atom of hydrogen and another circle to represent the second atom of hydrogen. Oxygen, similarly, to differentiate it, we shade oxygen. One of these red one represents one atom of hydrogen because there are 2 hydrogen atoms. Remember, in hydrogen, the bond is they bond covalently, double bond. Why? Because each atom will contribute 2 electrons. Each atom will contribute 2 electrons. Okay? Each atom will bring 2 electrons, then they share. In the overlap, there will be 4 electrons in the overlap. Okay? Okay, in the atmosphere. So the oxygen is like this. Is like this. Then for carbon dioxide, you see carbon also covalently bond with 1 oxygen atom to the right, and with double bond. Okay, they share. Each one will contribute 2. Also to the left, oxygen will contribute 2 electrons. Carbon atom will contribute 2 electrons. So the overlap between these 2, we share 2 electrons. Similarly, this way also on the right, we share 2 electrons. So diagrammatically, you use the black to show carbon. Carbon is actually black. And the oxygen, 2 atoms of oxygen, 1 on the right, 1 on the left. This O2 means 2 atoms of oxygen, 1 on the right, 1 on the left. So this is the diagram showing that. For methane, carbon is black, hydrogen is white. Okay, in diagram, and you can give a key to show which one is red, which one is black, which one is white. Okay, so on the top of hydrogen, because methane is like this, you have C, then bottom bonded with 1 hydrogen, right bonded with 1 hydrogen, top bonded with 1 hydrogen, and left bonded with 1 hydrogen. So this is for methane. Is that okay? Now let's move on quickly. So when simple molecules are represented using colored atoms, a key is used to show the colors for each of them. So that's just that. We've already said that. And let's take a look at, but before we go to work example, let's listen to a tutorial for 1 minute. Okay? Okay, before the tutorial, I think we can still do 1 or 2 things. Okay, let's take a look at this. Say, what is the molecular formula of the following compound? How many carbon do we have? How many carbon atoms? We count 1, 2, 3, 4. So there are 4 carbon atoms. How many hydrogen atoms? 4 on top, 4 at the bottom, that's 8. 1 right, 1 left, that's 10. So we can simply write the molecular formula. There are 4 carbon atoms. I write C4 and H is 10. So I write H10. This is butane in organic chemistry. Okay, this is butane in organic chemistry. So this is the molecular formula. This will be the molecular formula. And this one you see is called the display formula. This one we're seeing now is called the displayed formula. Is that okay? This is the display formula, this is the molecular formula. It's the same thing. One is display formula, the other one is the molecular formula. Is that okay? Now we move on to the second step. Before we go to the second step, the empirical formula, before we study the empirical formula, let's take a look at a short tutorial. Okay, now let's listen to this tutorial.
In this video, we will be looking at how to write the formulae of ionic compounds. You will have already learned in this topic that ionic compounds are made up of metals and non-metals and are held together by strong electrostatic forces. Overall, these compounds are neutral, meaning they have no overall charge. In order to write the formulae of these compounds, you should know the charges of the common ions. Let's start by having a look at a simple example of sodium chloride. You will know that sodium has a 1+ charge and chloride has a 1- charge. Therefore, these charges are equal and opposite. Therefore, we can just write the formula as NaCl, as the charges cancel each other out. The overall net charge is 0. It is not always that simple, and an alternative method for writing a formula is the swap and drop method. This can be useful in an exam as it is an efficient method of writing a formula when you have different and opposite charges. Sodium oxide is a good example. Sodium has a 1+ charge and oxide has a 2- charge. To use the swap and drop method, you can follow the following sequence. Having written the formula for each ion, drop the charges down to the subscript position and swap them over. Remove the positive and negative charges, and then put the ions together. So now we have the formula for sodium oxide as Na2O. We have 2 sodium ions, each with a plus charge, and 1 oxide ion with a 2- charge. These charges add up to 0. Finally, you will need to check for brackets, but we will come on to this in the worked examples. Make sure you write your numbers as subscript, which means just below the line of text. In these worked examples, you are asked to find the formulae of the following ionic compounds. For magnesium bromide, write out the ions. Magnesium, being a group 2 element, has a charge of 2+. And bromide has a charge of 1-, as it is a group 7 element. These charges are different and opposite, which means we can use the swap and drop method. So, swap them over and drop them down. Remove the charges. There are no brackets needed here, so the formula is MgBr2. This scores you 1 mark. Let's double check the formula is correct. We have 1 magnesium ion with a charge of 2+, which is cancelled out by 2 bromide ions, each with a charge of 1-. These add up to 0. Next, you are asked about lead-2 oxide. You can use the same starting point. Write out the ions. We know that lead is 2+, as it tells us in the name. Oxygen is in group 6, so when it becomes an oxide ion, it has a charge of 2-. As the charges are equal and opposite, the formula can be written out simply by removing the charges. So it is PbO. The 2+ and 2- charge cancel out to form a neutral compound. The correct formula is worth 1 mark. You can apply the same method for sodium sulfate, but here just be careful, as the sulfate ion contains more than 1 atom. Treat the sulfate ion as a whole and don't be tempted to alter it. Write the ions and charges down, swap and drop again, then remove the plus and minus symbols. As you can see, the formula is now Na2SO4. 2 sodium ions with a charge of 1+ are required to cancel out the charge of the sulfate ion. You may remember that earlier in the video we mentioned the use of brackets. In this example of calcium nitrate, they are required, and we will look at why. Start by writing down the ions for the calcium and nitrate as normal, and again, swap and drop. Now remove the charges, and we are left with CaNO3,2. Now this looks like there are 32 oxygen atoms in the formula, which is just not the case. We can show that there are 2 nitrate ions by adding brackets here. This again scores 1 mark. And finally, you can check your answer by adding up the charges of each of the ions in the formula and making sure they equal 0. In summary, you need to be able to write the formulae for ionic compounds. Remember that ionic compounds should be neutral in charge. If the charges are equal and opposite, the ionic formula can be written out simply. If the charges are different and opposite, you can use the swap and drop method, and you may need to include brackets. Make sure the charges from the positive and negative ions add up to 0. Don't forget to...
Okay, so we've just seen how to create a formula, a chemical formula for a compound, right? So if we have a compound, how we can easily write the chemical formula. Is that okay? Now, let's take a look at this empirical formula. Let's quickly take a look at this empirical formula, and then we'll come back. Do this one first. Okay, sorry, before we do the empirical formula, I think we do this one first, because it follows, right? Follows with the tutorial. Okay, now quickly, we do the deductive formula of ionic compound. We do this one first, then we'll come back to empirical formula and molecular formula in the end. Okay, now we say metals and non-metals, they react together to form ionic compound, right? So metals, they are positively charged because they lose electron. When atoms lose electron, they become positively charged. Non-metals, they gain electron. Non-metals, because they gain electron, they will become negatively charged. This one will become negative charge, like chlorine, for example. You have chlorine minus. You'll be wondering why is there minus, because you gain electron. When you gain electron, you become negative charge. Why are you negative charge? Because you now have more electron than proton in your nucleus. These metals, why are they positively charged? For example, like sodium, is positively charged because when you lose electron, your electrons, number of electrons and protons are same. But when you lose electron, your electron is now less. Your proton is now more than your electron, so you become positively charged. So this is what happens to ions. This is what happens to metals and non-metals, and they form ionic compound. When they form ionic compound, okay, ionic compounds are not simple molecules. Okay, they are not just simple molecules. So let's take a look at them. Let's remember, molecules are formed when non-metals, they react together to form compounds, right? Molecules are formed when non-metals react together to form compounds. But ionic compounds involve metals losing electrons and the non-metal gaining the same equivalent electrons that the metals have lost, okay, to form ions. When metal lose electron, they form ion. When non-metal gains electron, they form ion, like I have shown here. Metal lose electron, they form ion, positive ion. Non-metal gain electron, they form negative ions. Now let's take a look at some of the ions that are formed. This one you need to know off heart. Okay, hydrogen is +1 because if you lose one electron, okay, you lose this electron and become +1. All group 1 are +1. For example, lithium, lose one electron. It has one electron in the atmosphere, so it can easily lost it. That's what it can give when it's you look for any atom that is looking for 1, a non-metal that is looking for 1, like chlorine, that is looking for 1, okay, like fluorine, that is looking for 1, and then you react with it. So lithium, sodium, if you are group 1, you have 1 plus. If you are in group 2, you have 2 plus. That means you lose 2 electrons. And magnesium is in group 2. So if you are writing for magnesium, magnesium is in group 2. So if we are writing for magnesium, it will be Mg2 plus on top, right? Because in group, if we are writing for aluminum is in group 3, meaning it has 3 electrons in the atmosphere. So you can lose those 3 electrons in the atmosphere. It becomes Al3 plus. Okay? So you should know all of this. Is that okay? It's very important. Then the group 7, like fluorine, chlorine, fluorine, chlorine, bromine, iodine, they are in group 7. So meaning they are looking for only one electron. Because they are in group 7, they are looking for only one to complete 8. They're looking for one electron to complete 8. So that's why they have -1. Because they only gain one electron. Is that okay? That's why they have -1. Is that okay? If you are in group C, like oxygen, you have -2. Because you're looking for 2 electrons. If you're in group 6, you have -2. If you're in group 5, you have -3, like nitrogen. Nitrogen is in group 5. So you have 3 minus, because you're looking for 3 electrons to complete the outermost shell electrons, right? Then, copper, once they write copper 2 ions, meaning it's 2 plus. If they write iron 2 ions, okay, because transition method can either be 2 or 3, okay? Okay, so copper 2 ion means like when they say copper 2 ion, it means you write copper 2 plus. Copper 3 ion, you write copper 3 plus. For example, if they say iron 2 ion, you write iron 2 plus, meaning to lose 2 electrons. They say iron 3 ions, means you lose 3 electrons. So we need to know all this one. Then it's easy for us to write the formula of any compound. Then these ones are for metals and non-metals. What of about some polyatomic substance? Polyatomic means they have more than one element forming that ions. More than one element forming that ion. Okay? They have more than one atom or element forming that ions. Okay? A good example is carbonate. Carbonate is CO3 2 minus. You need to know this off heart. CO3 2 minus. Sulfate is SO4 2 minus. Hydroxide ion is OH minus. Nitrate is NO3 only minus, meaning only raised to power -1, only -1, only 1. Nitrate, only nitrate. If you like these patterns, CO3, SO4, only NO3 has only 1 minus. Okay, OH and with OH, right? The ammonium is +1. It's +1. Is that okay? So once you know this, they are very basic. 1, 2, 3, 4, 5. Once you know these 5 and you know these ones, then you can write the formula of any compound. You can write the formula of any compound. How to determine the formula of ionic compounds? How do you determine the formula now? There are 2 methods. We have the direct comparison and we have the swap and drop method, right? Ionic compounds typically have no overall charge. They don't have overall charge. What that means is that the size of any positively charged ion is cancelled by the size of any negatively charged ion. Okay, now there are 2 methods of determining our chemical formula. One is direct method. One is called the direct comparison. One is called the direct comparison. Okay. Now, the formula of an ionic compound can be determined by directly comparing the charges of the ions. Okay. We just compare the charges of the ion. First, let me show an example. For example, we say iron 2 sulfate. We have iron 2 sulfate. Okay. Now you write iron. You write iron. Iron 2 means Fe 2 plus. F2 2 plus. Sulfate, right? We already showed the sulfate. SO4 2 minus. SO4 2 minus. Okay, so the direct comparison you can see here is 2 plus 2 minus. Plus and minus, they are same number and same opposite sign. When you have same number opposite sign, then they cancel out. So it will appear that these 2 plus will cancel out these 2 minus. So the formula simply become, this formula of iron 2 sulfate simply become FeSO4. Simply become FeSO4. Okay, for direct comparison. Direct comparison is when we have equal magnitude, equal number of the ions. If they are same ions, then we use direct comparison, meaning they just cancel each other out. You have the formula like this, FeSO4. Is that okay? For direct comparison. So because you have 2 plus, 2 minus, plus and minus will cancel, and then there will be no ions, and then the formula become FeSO4 like this for direct comparison. Now what about the swap and drop method? The swap and drop method is to write the formula out, and you use the swap and drop method if you see here we have 2 ions, right, for copper 2 chloride. For copper 2 chloride, because they say copper 2, you write 2 plus on top of copper. Chlorine has only 1 ion, so you can see that they have opposite sign, but they don't have the same number. The magnitude are not same. Since the magnitude are not same, we do cross. Okay, we go to cross. We write copper 2. We write copper 2 plus, and then you write chlorine minus. You write chlorine minus, right? So here we cross multiply. So we bring this minus. This minus means minus 1. So we cross it over this way. So we give it to copper. We cross it to copper. Copper will now be only Cu. Only Cu1, right? And like say we can ignore the plus and minus. And then you bring these 2, chlorine Cl. We cross these 2 to the chlorine side. We cross it to the chlorine side. These 2 here, we cross it. We drop the sign, the plus and minus. So we get CuCl2. So this becomes the chemical formula of the copper 2 chloride. This becomes the chemical formula. So we must learn how to write chemical formula. It's very important for us to progress in chemistry. Is that okay? Now let's take a look at this question. Say the compound produced in the reaction between iron wood and chlorine contains iron 3 ion and chlorine minus. You give the formula of the compound and state the name of the compound. Now the formula will be, we write iron 3 ion and chlorine minus. Then the next thing we do is to cross multiply. This one is minus 1, so we bring the minus 1 here, but we don't write the sign. To be honest, you just ignore the sign. You bring the 1 here. But in chemistry, maths, physics, if something is 1, don't need to write it, right? Then we cross this one here over this way. We cross this one to this way. And you cross these 3 here. So you bring chlorine, you bring your chlorine, and when you cross this 3 to this side, here become 3. So this becomes the chemical formula of the compound. Now the name will be iron 3 chloride. That will be the name of the compound, iron 3 chloride. Okay? Okay, so that's for how to name compound. Now let's go to the one we skipped, the empirical formula. Okay, let's quickly talk about the empirical formula, and then we call this the day. Empirical formula. Now let's take a look at empirical. Empirical formula is the simplest whole number ratio of atoms of each element present in one molecule or formula unit of the compound. Okay? Empirical formula is the smallest formula unit. For example, what do we mean by smallest formula unit? If I have C4H10, in the case of butane today, we talk about butane C4H10, right? You know we can reduce this one to small. This is a molecular formula. We can reduce it. 2 can divide here, 2 can divide here. So I can have C2H5. If 2 divide 10, we get 5. So C2H5 is the simplest. It's like when they give you small fraction, they say reduce it to the simplest 10. Okay, the simplest whole number ratio, not decimal. The simplest whole number ratio. Okay, is called the empirical formula. If they give you any molecular formula, once you can simplify it to simplest whole number ratio, that's called the empirical formula. Even if they give you, let's say we give you C20, H40, C20, H40. If we give you something like this, for example, if we give you something like this, they say, okay, this is a molecular formula. They say, determine the empirical formula. Empirical formula is to reduce this to the lowest term. So like these two numbers can divide themselves. So 20 divided by 20, I'll get 1. That means I have C1. 40 divided by 20, I have 2. So the simplest whole number ratio will be CH2. And this CH2 is the empirical formula. This CH2 is the empirical formula. So when they say empirical formula, they are talking about the simplest whole number ratio. Simplest whole number ratio of element present in a molecule or formula unit in a compound. The simplest ratio, the ratio here is ratio 1 to 2. You know, we've reduced this one from, see, the ratio was 20 to 40 in the molecular formula because carbon was 20, carbon atoms were 20, and hydrogen atoms was 40. Okay, carbon atoms were 20, and hydrogen atoms were 40. Now, what we succeeded in doing, we've reduced this to the simplest whole number ratio, meaning I divide here by 20, divide here by 20. Now we got ratio 1 to 2. We got ratio 1. We got ratio 1 to 2. We got ratio 1 to 2. Okay, so this ratio 1 to 2 is what you have here. C is 1, that's why we write only C. And hydrogen is 2, that's why we write H2. This is called the empirical formula. This is what we call empirical formula. Empirical formula is the simplest whole number ratio of elements in a compound, of atoms of elements in a compound. Empirical formula. Is that okay? Okay, so now we understand what empirical formula is. The molecular formula is the normal formula of that compound. The normal formula of the compound. Is that okay? Now, the empirical formula of an organic molecule is often different to its molecular formula or the chemical formula. Yes, because the empirical formula is the simplest whole number ratio. You can take a look at this chemical formula or the molecular formula. This is, we call this structural formula. Okay, and this is the molecular formula. This structure, we know we have structural formula, display formula, and molecular formula. This is a molecular formula, this is a structural formula. Now you count how many carbons are here. 1, 2, there are only 2 carbons. And how many hydrogens are here? 3 plus 1, that's 4 hydrogens. That's what you see here. And how many oxygen are here? 1, 2. That's what you see, O2 here. So this is the molecular formula. This formula and this formula, they are same. Just that this is the structural formula. This first one is the structural formula, while the second one is the molecular formula. And if we ask you for the empirical formula, you can see 2 can divide all. So this one divided by 2, I will get C. This one divided by 2, I will get H2 because it's H4 originally. So 4 divided by 2, I will get 2. There, oxygen is 2. 2 divided by 2, we get 1. So the empirical formula is now CH2. So this is the empirical formula. So empirical formula is the simplest whole number ratio of atoms in a compound. Is that okay? This is the structural formula. This is the molecular formula, and this is the empirical formula. Okay, you can see it here. They wrote it. The empirical formula. Is that okay? So that's it for empirical formula. So here, if we are asked to write the molecular formula, we fill this one up. How many carbon atoms do we have? 1, 2, 3. So we have 3 carbon atoms. So I write, for molecular formula, I write C3. I write C3. There are 3 carbon atoms. How many hydrogen atoms? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 hydrogen atoms. So I write this. Now, they ask us to write the molecular formula. This is the molecular formula of the compound. Now, they also want us to write the empirical formula. This one, you cannot reduce the ratio, and you cannot do decimal. You cannot say, oh, 3 divided by 3 is 1, 8 divided by 3, 2 point something, or whatever. You don't do that. So this one, since you cannot reduce it to simpler ratio, the smallest ratio is ratio 3 to 8. You cannot further reduce this ratio of carbon to hydrogen. You cannot further reduce it. It's only when we can reduce it that we reduce. If you cannot longer reduce it, if it's then the molecular formula will be same as the empirical formula. So our empirical formula for this particular compound will also be C3H8. The empirical formula will be same thing. Empirical formula will be C3H8. Is that okay? Because why? Why is that so? Because we cannot reduce this ratio. Okay. Now we go to the next one. Let's see. Here we have how many carbon atoms? We have 2. So we write C2 for the molecular formula. C2 and how many hydrogen? 4. C2H4. This is the molecular formula. Now by this one, if you look very well, we can reduce this ratio. Okay? Because this ratio 2 to 4. We can simplify this ratio further. We can simplify it to ratio 1 to 2. We can simplify it to ratio 1 to 2. So which means the empirical formula will be C1. C1 no need to write 1 and H2. This will be the empirical formula. Okay? This will be the empirical formula. Okay? This will be the empirical formula. Okay, but before I go, I will just okay. Anyway. This one, the molecular formula, you count how many C? 1, 2, 3, 4. So you have 4C. How many H do we have? We have 10, right? See 4 here, 4 here. We have 10 H. So H is 10. H is 10. And O is 1. O is 1, right? Yeah, O is 1. So this is the molecular formula if O is 1, right? If O is 1, this is the molecular formula. Then what's the empirical formula? Because we cannot change, it's the same thing. Why? Because we cannot divide the last O, okay? So our empirical formula will be the same thing. Okay? Okay, so these are the formulas. Okay, we've answered them here. You can see the molecular formula is same as because you cannot simplify this whole number ratio. They're same. Both the molecular formula and empirical formula. You cannot break this ratio down, or else you get decimal. And they say simplest whole number ratio. Whole number cannot be decimal. So it means it's going to be same. This one you see you can divide this one. This molecular formula, you just count number of carbon, you get this, number of hydrogen, you get this one. And then the empirical formula is to simplify this one to the simplest whole number. And then for this last one, you cannot do anything, so we just write what it is. Is that okay? Then later we're going to do empirical formula calculation. Okay, this one is just to show you the difference between empirical formula and molecular formula. Later we're going to do the calculation. Okay, so with this we come to the end of our today's class. Thank you for joining us.